Hi gang, here we are with the first of the video installments of lessons. So everybody cross their fingers, hope this helps us to all understand physics a little better. With this new style comes a new subject. We're now going to turn our attention to something called electrodynamics. Electrostatics is what we just finished. That was when you take a pile of electrons or protons and you place them somewhere, and then you examine what has happened by you placing them there. The electrons aren't moving anywhere. They're just sitting in a hump, or the protons are just sitting in a big lump. And after you put them there, they immediately, or nearly immediately, set up like an electric field and potential difference and all that stuff we studied. But nothing else really exciting happens after you've set them up. What's really exciting is when electrons start flowing, because then you can get things like cell phones and TVs and all kind of cool gadgets that we have. So we're going to turn our attention to electrodynamics, and with that comes a concept that we call current. That is electrons flowing somewhere. Whenever we introduce a new concept, it usually comes with a new formula and a new unit, and indeed this does. Current is abbreviated with an I. I don't know why we used an I. We were all out of the good letters. Current is abbreviated with an I. We certainly don't want to use C. That's already for coulombs and capacitance, and that'd be confusing enough. So current is I, and it is merely change in charge divided by change in time. Think of it this way. If I've got a wire and there's electrons flowing down the wire, then if I just pick a point on that wire and I count the number of electrons that go past in a second, that is the amperage. That is the current. Now the unit that we use is called the amp, after Mr. Ampere, who was the guy that developed all this. And 1 amp is equal to 1 coulomb over 1 second. 1 amp is 1 coulomb divided by 1 second. Remember a couple of weeks ago when we talked about how many electrons in a coulomb, 6.25 times 10 to the 18? We wondered why that weird number? Well, that number was weird so that all these numbers and units could come out to nice, usable things. Back then I told you I'll explain it later. Well, here I am now explaining it. So that's the formula for current, and let me say that current is the thing you want to watch out for. When I've told everyone you can test the voltage on a battery, a 9-volt battery, by licking it, and it's a mildly unpainful or unpleasant, but it's not painful. Well, you're getting just a few milliamps when you do that. What you don't want to do is stick a fork in a wall socket, because then you get much more than a few milliamps. You get a few amps, and a few amps can kill you. So amperage is really the thing that is important when being safe around electricity. Let me give you a feel for how many electrons we're really talking about. I looked up the other day an iPod has current of 35 milliamps. Milli, so I divided it by 1,000, 0.035 amps. I just applied this formula to it. 0.035 is equal to change in charge divided by 1 second, in an attempt to find out how many electrons are going down the wire in any given second. Down the wire from the battery in your iPod to all the electronic gizmos that make music for you. Oh gosh, doing that math was pretty easy. It came out, the units on charge is going to be coulombs, so it is 0.35 coulombs. But you remember, there are so many electrons in a coulomb. I did a unit conversion here. 1 electron is 1.6 times 10 to the minus 19 coulombs, and that means that in any given second, there are 2.2 times 10 to the 17 electrons running down the wires inside of your iPod. Just to kind of get that feel for that, if you were to look at 1/1,000,000th of a second, in that 1/1,000,000th of a second, roughly 500 million electrons flowed past a given point. So electrons are these tiny little things, and you got to get lots and lots of them moving in order to get anything useful to happen. So that's the basics of current. There's things you need to know about when we have current flowing, and here they are. I just bullet pointed them. No potential difference means no electron flow. You remember potential difference, and I use that 9-volt battery as an example. Potential difference is where you've got one region of space, the top of the battery, which has a different potential than the bottom of the battery. If you connect a wire up between them, electrons would flow from the low side to the high side, and I said, at least in theory, that protons would flow from the high side to the low side. Truth is, the protons aren't able to flow because they're locked up inside of the nucleus. But if there is no potential difference, there will be no electron flow. Think of it this way. If you took a garden hose and filled it with water and held both ends at equal height, no water would flow out of the deal. But if I lowered one so that it was at a lower gravitational potential, then I took my thumbs off, the water would flow out. Well, that's really what happens. If there is no potential difference, that would be battery in our case. If there is no battery, nothing will happen. You know that empirically. Your cell phone dies and you can't do anything until you recharge it. What recharge it means is get in there and somehow separate a bunch of electrons from a bunch of protons so that later when you turn your phone on, they can get reconnected in some chemical fashion. So no potential difference means no electron flow. You have to have a battery. Point two, electrons must flow in a circle. If I were to take a battery and hook a wire up to the end of it and put maybe a capacitor on there or some other assorted gizmos, nothing would happen. It's only when I then connect that wire back to the top side of the battery that something magical happens. You will never have electron flow if the wire kind of is just hanging out in space. It has to go in a circle. We call them circuits. It has the same root as circle. So electrons must flow in a circle. And number three, there is a difference between conventional current and electron flow. I wish this weren't the case. It's Ben Franklin's fault. When Ben Franklin was cooking up the idea of positive fluid, remember we talked about he thought there was a fluid flowing that was invisible and odorless and colorless, and it was flowing. There was some materials had more of the positive fluid and some had more of the negative fluid, and he thought when they came in contact they were flowing. Well, that was wrong, of course, but we're kind of stuck with the same terminology. Because he arbitrarily called one positive and one negative, we talk about positive flow of current. But in truth, you and I understand the periodic chart now, and we understand how it's electrons that are easy to move, and so it's really the electrons flowing. So, and again, it's 200 years, better than 200 years, and we're stuck with it. If I draw you a circuit, the current acts like it's flowing out of the top end of the battery, the plus side of the battery, down around the wires and back in the negative side. But really the protons are not flowing anywhere. It's the electrons that are flowing. So the electrons are moving against the current. It'll be confusing. It confused me for a number of years as I was studying this stuff. It's just one of the things we're going to have to just power through. I want you to know about it right now. One last concept on this video, and that is, well, it's got to be math, right? What fun would physics be if it wasn't for any math? We've already talked about capacitors, and I showed you a number of them. I've got to show you another little deal, and it's called a resistor. I got some of them in my hand. I hope they show up on the video. They're just these little wires that have little blobs in the middle of them, look kind of like ants. And you'll notice that those resistors, they have colors on them. I'm not sure how well that's coming up on there, but they've got little bands of color on them. Each one of these, I've got like a dozen or so in my hand, that's called a resistor. And the bands tell me something. When I bought that big pile of them, it came with this little chart. You see the colors there? The colors on that match the colors on this. And I can look at this chart and I can figure out how much resistance a resistor has. What is resistance? Well, whenever an electron is going down a wire, it's going to run into some resistance. There's other electrons in the way. It's going to kind of bump them out. And you can arrange it so that some atoms really don't want electrons to go by, and the more they desire the electrons not to go by them, the higher the resistance is of that particular item. Now, you also need to know that I say it's electron flow, but the actual electron, if you were to take one electron in a circuit and look at it, it is not going very fast at all. It is traveling at something like, maybe 1/10 of a millimeter per second. But yet, if I turn the headlights on in my car, the headlights come on immediately. If I were to, that's a great example. If I were to pull the switch and turn the headlight on in my car, and just as soon as I do that, an electron's going to start running out of my battery, and it's eventually going to get to the light bulb, and when it goes across that filament in the light bulb, it's going to make some light. Well, at 1/10 of a millimeter per second, that particular electron doesn't get there for over an hour, and yet the light turns on roughly immediately. That's because the electrons, while each one doesn't move much, they kind of bump the others along. It's kind of like if you've ever looked in a traffic jam. You're moving kind of at slow little paces, you know, with a couple foot here and a couple foot there. If some guy 100 cars in front of you hits his brake lights, you can see the brake light wave move very, very quickly. Well, it's the wave of electrons. As they scrunch up at one end, they spread out, and that travels at very, very high speeds, hundreds and hundreds and hundreds of miles an hour, but the actual electron doesn't move that quickly. That said, we measure the resistance on these things in something called ohms, O-H-M, after Mr. Olmsted. And because his name sounds like omega, the Greek letter, we abbreviate it with the Greek letter omega, capital Omega. It looks a little like a horseshoe. Hope you can see that on the screen there. And gracious, if we're going to have another unit, another thing we have to measure, then we've got to have some unit to measure it by. 1 ohm is equal to 1 volt over 1 amp. And yes, the day will come when I ask you to translate that back to SI units, so get ready already. 1 ohm is equal to 1 volt per amp. If I took one of these resistors, let's say it was a 1 ohm resistor, I could measure its voltage, and if it had 1 volt, that would mean that it was pushing 1 amp worth of electrons down it each second. Mr. Ohm, the way he did his experiments was he was able to measure voltage and current in a fairly accurate way. We're going to do some labs where we kind of roughly recreate his experiments. But he took a piece of wire and measured the voltage and the current, and then he doubled the wire, the length of the wire, and he measured them again, and he tripled it and measured it again. And he was able to experimentally determine a formula that now goes by the name Ohm's law. It's fairly straightforward. Voltage is equal to current times resistance. Voltage, V, is equal to I, current, that's the one we learned a few moments ago, times resistance. That's called Ohm's law, and we will do a number of problems with that, many problems with that. They will, actually, just after this video, I will record some sample problems with those. V equal to IR is Ohm's law. Don't pay attention to that right now. Well, if we're talking about electrons flowing down a circuit, you remember electron flow taught us about work being done. Potential difference is the work done per unit charge of a charge moving, in this case an electron. Well, if we're going to talk about work being done, we ought to talk about the rate at which work is done. You'll remember from when we were talking about work that the rate at which work is done is called power, and it is measured in, wait for it, what is it? I hope you all said it. It's measured in watts. Well, Mr. Joule came along. Remember him? He's the guy that got the unit of work named after him. Unit of work and unit of energy, the Joule. He came along and did a bunch of experiments here too, and he found out, well, let me start with one relationship. P for power is equal to current times voltage. He did that experimentally. It's a really cool experiment. I'll show you a video of it in class in another day or two. So the power drawn by an electrical circuit is equal to the current going in the circuit times the voltage, the potential difference provided by some type of battery or other electric source device. Okay, if you just hold right there, V equals IR and P equals IV. Those are fairly straightforward, but you know, it never stays straightforward. Mr. Joule took this and he said, okay, I've got V here, so I'm going to substitute IR in there for where the V was, and he was able to derive that power was also equal to current squared times resistance. And then he did it the other way. He said, let me divide this so current is equal to voltage over resistance, stuck it in here and got rid of current. Power is equal to V squared over R. That's 4 very straightforward formulas. They are on the formula sheet. On the website here, I have a fresh, updated copy of the formula sheet if you need it. But I want to point out we have 4 formulas here that we will do a lot of work with. V is equal to IR, Ohm's law, and three forms of power. Power is current times voltage, power is current squared times resistance, and power is voltage squared divided by resistance. Note that in this one, there is no reference to power, there is no P. Here, there's no reference to resistance, to voltage, and to current. Remember kinematics? Way back with kinematics, we found out the one thing that we neither knew nor cared about, and that was the thing that told us which formula to use. Same thing is true here. If you look at the sample problems that I will include in another video, you will see that it is easy to figure out which one of these to use, and you can do some real work. As a matter of fact, you can determine, I don't know, how much energy is going into your hairdryer, or what makes your toaster cook toast. So it's really usable stuff that should be, other than doing some problems, that's enough to get you ready for school tomorrow. So I will put a video of a couple of sample problems. You don't have to do them. You just have to follow along and understand them. I look forward to working some with you in class tomorrow. See ya.